So even though I've got the tail to head diagram drawn here, okay, kind of just so we can reference it, right? If we would have drawn this, okay, with the original tail to head, we have our 620 kilometer per hour one, okay, that was 40 degrees south of west. And then we had our 500 kilometer per hour one that was 75 degrees east of north, okay? That's how it would all look if it was all put together. But just because some people are saying that seeing that whole big picture is difficult, I'm actually going to solve this one entirely using the separate triangle method, so that if this is giving you trouble, you can kind of see one done completely with the separate triangle method. All right, so I'm just going to get all of this stuff and chuck it out of the way for now. Oh, I didn't want it to go over there. Okay. So we're going to draw this with the separate triangle method, okay, really quickly. We've got west of south, okay, as one of our vectors, so I'm going to draw a line that's south. I'm going to go 40 degrees west of that. Okay, scale doesn't matter when I'm using this method. Here's y, here's x, because I'm not actually putting them together, right? So I've got 40 degrees west of south, this being 620 kilometers per hour. Okay. Our other vector is 500 kilometers an hour at 75 degrees east of north. So I'm going to draw a reference line that's north. I'm going to go 75 degrees east of that. Okay, this will be x, this will be y. Here's the 75-degree angle. This is 500 kilometers an hour. Okay, so I've got those two triangles drawn separately. They still look the same as the two triangles that are in the big diagram. Okay, and they are, but they're not together. Okay, I'm still going to get all the same mathematical stuff I got before. Okay, so I'm going to solve for black x. Okay, it's the opposite side here, so that'll be the sine of 40 degrees times 620. So sine of 40 times 620. Okay, so 398.528. Be kilometers per hour west. Okay, then I'm going to calculate black y, which will be the cos of 40 degrees times 620. Okay, so 474.947. Okay, and that is going to be kilometers per hour, and that is south. Okay, so got my x and y components for the first triangle. Now I need to do the same thing for the second triangle. Okay, so red x is the opposite side, so it'll be the sine of 75 times 500. Okay, so it's 482.962. And that is going to be kilometers an hour east. Okay, and then y is the adjacent side, so it'll be cos of 75 times 500. Okay, so we got 129.409. And that'll be kilometers an hour, and that is north. Okay, so far, all the math looks the same as if I had drawn it the other way, because it is the same. These are the same vectors. Okay? Whether I draw them tail to head or I draw them separately, they still have the same x and y components as they would if I drew them the other way. Okay? That's why there's absolutely no problem with doing this way. Here's where the drawback is. I don't see the big picture. Right? That's the advantage if you don't like looking at it that way, but it's a disadvantage for me who does like to see the big picture. Okay? I don't know what my resultant looks like yet. I actually have to build it. So first I have to calculate my resultants x and y. Okay? So on the big diagram down here, that would be finding blue x and blue y. I don't know what that looks like yet because I don't have this diagram technically, even though I have it down here. Okay, everyone follow me there. So I have to build that triangle without really knowing what it's going to look like. So once again, I'm just going to move this further down so it's out of our way. All right, so now that I've got all of this stuff, I need to calculate my resultants x and my resultants y. Okay, so I'm going to move up a little bit. My resultant x, okay, is going to be the 398 kilometers per hour west plus 482 kilometers per hour east. In other words, I've got to subtract them, right? So I'll have my 398 minus my 482, okay, obviously with all the decimals in place. Okay, so 398.528318 minus 482.9629131. All right, so I end up having a resultant x component that is west 84.4 kilometers per hour. Kilometers per hour west. Okay, I need to do the same thing to calculate my resultants y component. Again, I don't know what it looks like, so I'm just calculating them here. Okay, so to calculate my resultants y, I'm going to take the 474, okay, that was south, so it's negative, okay, and add the 129 that was north to get my resultant there. Okay, so I'm going to have 129.4095226. Okay, so that's north minus south, which was going to be the 474 here. 0.947547. All right, so I end up being quite a ways south, 345 kilometers per hour south. And kilometers per hour south. All right, now that I have those two numbers, now I can draw my overall resultants triangle, okay? And wait a minute, I got one of these numbers mixed up. This should be east, right? I did that wrong. This one's west. The big one was east. Sorry, that should be east. I screwed that up. Okay, so when I'm drawing this now, I'm going to draw my east component or x component. It's 84. Okay, so 84.4 kilometers per hour, okay? And then I'm going to draw my south one, okay? And it's 345, so it's much, much longer, obviously. Okay, something like that, 345 okay, kilometers per hour. And that's south, and then that gives me this resultant. So here's theta, and this would be my average velocity. Okay, looks pretty much like the triangle I drew before in the big diagram, except I came to have it differently. Okay, without arriving at it visually, I arrived at it mathematically instead. Okay, but it ends up being the same regardless of which way I do it. Now, to calculate my average velocity, that's going to be Pythagorean theorem, so 84 squared plus 345 squared. Okay, will give me my overall resultant here. Okay, so plus my 84. Plus 400.13 squared. All right, so my overall resultant is 3.6. I think I only have two significant figures here, right? Yes, just two. Okay, so two significant figures, so I'm gonna have 3.6 times 10 to the 2 kilometers per hour, and then I've got to find my vector. Okay, so my vector is right there. The 345 is opposite, so I'll have 10 to the minus 1 of the 345 over the 84. Okay, and when I do that, I think it's 76 degrees, right? East of south, or sorry, south of east. Okay, so my final answer, 3.6 times 10 to the 2 kilometers per hour at 76 degrees south of east. Okay, that would agree with my diagram, but I arrived at it mathematically instead of visually. All right, so if you find that way works for you, just visually, then go for it. Okay, mathematically they're the same. Okay? I do all the same calculations regardless of which way I draw it. Right? And that might, for some of you, that might help you speed up how quickly you do the vector addition problems, because you're not worrying about, is the diagram to scale, is it right, are these things pointed the right way? Just draw them separately, scale doesn't matter, okay, and then you can solve them that way. All right, second part of that question wanted to know, okay, what's the displacement if the plane flew for 7.5 hours? Well, that's just this calculation here. We just calculated V. We know the T is 7.5 hours, so we take our 3.6 times 10 to the 2 kilometers per hour, multiply by 7.5 hours, and we'll get 2.7 times 10 to the 3, that should be kilometers, at 76 degrees south of east. Okay. Everybody with me on that one? So obviously we're giving you some tricky ones here, lots of backtracking, okay, that kind of stuff, but I mean that's what we have to be able to do. All right, so no questions on 14? Okay, I want you to try this one. Don't worry about B, but I want you to try this one because on your assignment tomorrow, there's a question that's just like this, except it's about golf instead of football. Okay, it's 3 vectors. Okay. 3 vectors. One of them is straight, so you don't have a lot of calculating to do with it, okay? But you have 2 that are angled. Okay? Give that one a try. This, okay, so if we're drawing this one tail to head, right, we have our first one that's 10.5 meters at 25 degrees south of west. Okay, so I'm going to draw a reference line that's west. I'm going to go 25 degrees south of that. Okay, so this is my 10.5 meter line. Okay, here's X and here's Y. Okay, then I'm going to have another one. This one is 15 meters at 20 degrees west of south. Okay, so 20 degrees west of south, and it's a bit longer. It's 15 meters. And then my last one is 8 meters due south. Okay, so that's what my diagram would look like with my resultant obviously going from beginning to end. As long as you're close, as long as it's generally the right shape, you can't really go wrong from there. Okay, so that's our overall displacement. Okay, got to find your y's and x's and all that. So that's the diagram.